just because again, moved like, thing around. Okay, cool. Nope, that's not what I want you to do. Okay. So in a single lecture, we managed to cover all the integration techniques that we want to. Great. No more integration techniques. Except for like your next assignment, where I kind of make you do one. I don't remember. Maybe I do, maybe I don't. Okay, but we're basically going to start kind of a new, I don't know. We'll see. It's not too bad. I actually think, no, the first one, I make you prove a little theorem that we already proved in November. So I make you reprove it, but now with integrals. So that's not too bad. The second one is a trigonometric reduction formula, which is pretty slick. Like for the most part, it's just a computation, but there's a little trick to it, but it's not crazy. It's not too hard. So maybe I'll leave like the new integration techniques to test or something. We'll see. So we're going to start on, trig happens sometimes in life. What are you going to do, right? We're going to start on improper integrals. Now, I think, I'm trying to remember how much time I budgeted for this. This one is, there's a lot of things that can happen in this section. And I think if you try and attack it from a memorization viewpoint, it's not going to go super well. So just, try and conceptually, arrange it and understand it. We'll see. You tell me. All right, so we're going to talk about improper integrals. Okay, so improper integrals, generally speaking, is when we try to integrate either functions that are unbounded or on domains that aren't bounded, right? So we know in order to integrate, both those things have to be bounded. Maybe we can say that. So to integrate, right, we must work with bounded functions. And bounded domains, right? So because we work on like the interval AB. Okay, so now we want to extend that notion, right? We want to be able to work with unbounded functions and unbounded domains. So improper integrals extend integration to unbounded functions and sets, or let's say domains. I guess that's what I've been calling them. Okay, so we're going to basically attack each of them separately. In theory, you could do them together, but that gets a little bit trickier. So we'll try and do them separately. So the first thing that we're going to do is unbounded domains, because I think that one's kind of more appealing. So let's deal with unbounded domains. Okay, and we'll just go straight into a definition for this one. So definition. All right, so we need to kind of, again, talk about the notion of integrability, but I'm just going to be lazy. So a function f mapping a infinity to r for some a, basically we don't care, is said to be integrable maybe I should just square bracket off that a, is said to be integrable if it's integrable on ax for all x. For all x in a infinity. So basically, it doesn't matter where you want to put the end right point. You can always do it and your integral makes sense. Okay. Then we define the improper integral. So that's the definition of integral. The improper integral . to be this thing. This is going to be the integral from a to infinity of f. So that's just notation right now. And that's going to be the limit as x goes to infinity from a to x of f, like this, if it exists. Or I guess we could say it's always equal to this. Some cases that just might not exist, but whatever. If this limit exists, we'll say that the improper integral converges and diverges otherwise. So if this limit exists, we say the improper integral converges and diverges otherwise. Okay, so we're always going to say, in this case, that the improper integral is this thing, and this number just could be infinity, could be negative infinity, could just not exist, right? That's totally fine as well. And then we're specifically talking about convergent. Oh yeah, sure. Yeah, thanks. That should be a open infinity. Okay, and then I don't want to rewrite all of this as you go to negative infinity, but it's the exact same thing, right? So maybe let me put that in like green. So note, mutatis mutandis, change what you need to. For the integral of negative infinity to a. Okay. And there is probably a good question at this point is there notion of a two-sided improper integral? So you go from negative infinity to positive infinity, and the answer is absolutely, that does exist. But it does have a slightly different definition. So, we have to attack these sort of, it's like limits, right? It's like a one-side limit. And then if we want to talk about a two-side limits, it's done in terms of the one-side limits, right? So if it's integrable on its domain, we say it's improper. Depends what you mean. So we're just going to say it's integrable if it's integrable on basically every subset of its domain. But that doesn't, in this case, for the improper integral, being integrable does not mean that your improper integral converges, right? So the improper integral is the value of this, which could be infinity, could be just does not exist. So that is the improper integral, but the function is integrable if it's integrable on every compact subset, right? On everything that looks like this. So you can be integrable and not have your improper integral exist, and that's okay. Though we could probably create a definition of improper integrable, being that this limit converges. We could do that if we want. But we already have a word for that, right? It's converges. Though again, depending on the situation, it might be nice to have an adjective for that. Needs to have a limit. Oh, okay, yeah, great. So Adam, this is a great thing. Yeah, that's absolutely going to be true to an extent. So that one's like morally, that's what's happening, right? It does appear that the function has to go off to 0, but it turns out that limit actually doesn't have to be equal to 0. It can't be equal to anything else. Like it can't be equal to 1, because if it's equal to 1, it certainly won't work. You'll somehow accumulate like infinite amount of area, but it is possible for the improper integral to exist and for that limit to simply not exist, right? And what I want you to do, actually here, I'll give you an example of it. So let's do like a really quick example. Okay, so I actually hadn't originally intended to do this example, but we can. So determine if the integral from 1 to infinity, 1 over, let's say, x to the 5, converges, and if so, find its value. Right, and by value there, I mean improper integral. And of course, those are doing the same thing, right? Like if you find if you find that this exists and you find its value, you've proven it exists. Okay. Now, let's be careful here. Again, everyone, I don't want you to plug in infinity into anything, and you have to be careful carrying this around. This is something that I had to give my 257 students hell for because they got a little bit lazy and needed to be, smacked around a bit. So when we evaluate this, we're evaluating a limit, right? So evaluating the limit, it is very tempting to carry the infinity around, but you can't do that. Right, so always go to here. So this is the limit. Sometimes we use b. Maybe I'll use b here because now I'm already using x. Right, make sure that you write that in terms of a limit. And now let's evaluate the integral because we can do that. B goes to infinity. All right, so what am I going to use here? So if I integrate this, what is it going to be? Negative 1/4 x to the negative 4. I hope somebody double check me. Make sure I didn't differentiate it. Okay, and I can plug everything into that. So that's going to be the limit. This b goes to infinity. I've got this minus sign I don't like, so I'm actually going to plug in 1 first and get rid of the minus sign. So that's going to be 1 minus, well, let me pull out the 1/4. 1 minus 1 over b to the power of 4. And you don't have to epsilon delta this, like, 1 over b to the 4 goes to 0 as b goes to infinity, right? So I get an answer of 1/4. Okay, now, Adam, you're saying like, okay, this function definitely, right? It seems like it's going to 0, totally cool. So that kind of completes that example. However, what I could do is I could modify this function in a slight way which breaks the limit, right? So note, so what I'm going to do is I'm going to take this function now. Let's take from 1 to infinity to r. Okay, and it's going to be 1 over x to the power of 5 if x is not an integer, and 1 if x is an integer. Okay, so you can check the improper integral of this function exists. And it has the same value, right? Because when you get to this part right here, for this function, it doesn't care about what happens at the integers, right? Like from 1 to b, for any fixed b, that's a measure 0 set. So the function being equal to 1 there isn't going to affect the integral at all. And that's true for any b. So the entire computation is effectively the same. And you end up getting that this thing, exists, it converges and has a limit of 1/4. But the problem is that this function does not have a limit as you go to infinity, right? Because no matter what you do, it's always going to leave your epsilon band around 0, right? You put a little epsilon band around 0. Well, every integer, it just pops out for a second in order to say hi to the number 1. But as a result of that, right, your limit doesn't exist. So this is one of those things where you want to say like morally it's going to 0, right? That as you go to infinity, but for technical sort of silly pedantic reasons, on a measure 0 set, I can make sure it doesn't go to 0, but that's enough to break the limit, right? So you need some sort of like way of talking about the limit except on a measure 0 set. We don't really have that ability, but yeah. So again, morally you have the right idea, but it turns out that you can sabotage things a little bit. Okay, does that make sense? Cool. Right, now your idea is absolutely true. At some point we're going to start talking about sequential limits, right? So we'll look at sequences instead of functions. And when we deal with sequences, your intuition here will absolutely be correct, simply because you don't have this, infinite data to play with. Sequence is only defined over the natural numbers to begin with. So if you start to do weird things on a discrete set, you kind of break the overall behavior of the sequence. So your intuition is correct when we get to sequences, and it's morally correct for functions. But yeah, like I said, strictly speaking, we can break it. Okay, so I hadn't planned to do that one. So maybe what I'll do, oh no, I've probably got some time here. So maybe I'll do this one quicker. This was my original planned example, because that one's kind of boring, right? Like that one's pretty easy. Could the function not be integrables on some intervals, yet still have a limit? That's going to be tricky. Because, yeah, okay, let's see. What could happen? So strictly speaking, by the definition, the problem is that when you take a limit, right, over here, you're taking a limit over the interval 1b. And if at any point you encounter an interval that is, on which your function isn't integrable, it stays in there forever, right? So somehow what we would need is that something was able to cancel out the non-integrable portion, but I don't think that's ever going to happen, because the only thing that we're doing here is we're expanding the integral, right? Or the domain over which we're integrating. So I don't think we're ever going to have a situation where we can kind of like cancel that behavior. So that's an interesting question. I'm going to say in this case, probably not, right? There are, for example, there are examples of functions which are not integrable that when you add them, they are integrable, right? That's totally a thing. But yeah, in this case, I'm gonna say no, right? Like I'm fairly confident that, yeah, if you just fail to be integrable on some interval and your improper integral, contains that interval, then you're in trouble. Of course, if you don't, right? So for example, 1 over x to the 5 is not integrable in any domain that contains 0, but you can see as long as we kind of ignore that domain, right? As long as we ignore 0, we're okay. So in that case, yeah, we're fine, right? But yeah, if your improper integral contains a domain in which you're not integrable, yeah, I'm going to say with a great deal of confidence, it probably won't work out. It's 1 minus 1 because the square brackets is when x equals 1 and x equals b. Exactly, yeah. So just like I was asked about this like vertical line. So we do the same sort of thing. I guess, yeah, let me clarify this notation right here. This is the same thing as the vertical line, is that when you write something in brackets, usually we use square brackets. When you write something in square brackets and you use the like superscript and subscript like this, it means same sort of thing. We're going to plug in. Oops. This also means f of b minus f of a. Yeah. I guess, is this the first time I've used that notation? It might be. Okay, sure. Yeah, so it's the same sort of thing. Exactly the same sort of thing. So let's suppose we take the limit as x goes to infinity. Adam, what's that part right there of f equals 2? Oh, like if the limit of as x goes to infinity of f is equal to 2. Can we say that the limit of the integral is 2x? Like the improper integral for sure won't exist, right? Yeah. But no, yeah, you can't use the value of the limit to determine what the integral will be. But if the original function does have a horizontal asymptote and it converges to something which is not 0, then it definitely doesn't exist. So actually, this is an interesting proposition. So I love this. I love that we're sort of like hypothesizing our propositions. So let's try this. So if f maps a infinity to r is integrable, and the limit as x goes to infinity of f of x is equal to a for some a, not a, because I've already used a, it's L, for some L not equal to 0, right? Then the integral from a to infinity of f diverges. Okay, this I think will be a good exercise. Maybe I'll prove it next time. Let me think about how this one goes. But for sure, if the limit is not 0, then it won't converge. Basically, I think your technique here is going to be the same sort of thing that we've done in the past, where you say, listen, if it approaches L, then you can guarantee beyond some point everything is within, some L minus epsilon band. Right, so this is how my first attempt at proving this. I'm going to leave this as an exercise for you. And then if there's enough questions, maybe I'll come back to it. So let's say you've got this sort of function and it does something like this, right? So it's converging and it's converging to, I really like though when you guys kind of come up with your own propositions. That's nice. So it's converging to this point L. So beyond some point, everything's within L minus epsilon. So let's take like epsilon to be L over 2, right? So something like set epsilon to be L over 2. So that means that everything is within 3L over 2 and L over 2, right? That's our epsilon band. Okay, so beyond some point N, the function is always inside of, maybe let me solidify these bands, is always in the solid band range. So now what you can do is compute the lower bound, like the lower Darboux sum here. And you can say whatever the value of the integral, it's going to be bigger. Like when you take the supremum will always be bigger than L over 2. And you can show now that L over 2 becomes arbitrarily, or like the lower sum becomes arbitrarily big. Does that make sense? Does everyone see what I'm saying here? So you can do like we did with the log, is basically just start taking integer partitions. And when you compute the lower sum, you can say, well, the lower sum for sure is going to be bigger than these rectangles, right? Because you're guaranteed that the function actually lives in that band, and we're using the lower end of that band as our approximation. So the lower sum, say from like, n to, again, you have to make sure these things kind of like integer out, but that's not too hard. So you'll get something like the lower sum of f on the interval n to n plus k of your kind of silly partition is equal to, what is that going to be? K times L over 2. And so your integral is going to be bigger than this. And well, as K becomes very, very big, this in turn forces the integral to become arbitrarily big as well. So you can guarantee now that the integral of the function doesn't converge anymore, right? And that's going to break it. So I think this should spell this out. So I'm going to say, try this as an exercise. This proof is actually much easier when you're doing it with sequences versus if you're doing it with functions. But yeah, try this as an exercise. I'm pretty sure what I just labeled here is the proof. Like I've almost done it for you. You just kind of have to write it up and convince yourself that it works out. But yeah, give that a shot and see if you can make it work. Okay, so if you want, then you can use that proposition. Like I said, see if you can prove it. Okay, but again, notably, the converse is not true, right? As we just illustrated, if the integral converges, it doesn't guarantee that the limit exists and is equal to 0, right? Oh man, I keep accidentally turning off my surface. Okay, so give that a shot, see if you can do it. Note as well, you can absolutely be asked to do integration techniques. Here, I'm going to be lazy and I'm just going to say determine. What did I do? 0 to infinity. Right, and by determine again, I mean, determine if it exists, determine if it converges, if it diverges, if it converges, determine its value. And like, we set up like always, right? So the integral from 0 to infinity. Don't forget to put your limits in. Okay, I'm going to use a substitution. let u be t squared plus 1. Du is 2t dt. So this will become the limit as b goes to infinity. All right, what do I need to change my things to? So this is going to become 1/2. This is going to become 1. This is going to become b squared plus 1 of 1 over u squared du. Limit as b goes to infinity, 1/2 of negative 1 over u. And again, I'm going to use my kind of weird notation here. 1 over b squared plus 1. Again, that's universal. This actually is a fairly constant or consistent notation. You can totally use this yourself. B goes to infinity, 1/2. Same sort of thing. I don't like the minus sign, so I'm actually going to plug the bottom number in first. And yeah, again, you're right. Don't do epsilon delta this. You know 1 over b squared plus 1 is going to go to 0. So we get 1/2 like that. Right. So totally, you might have to use an integration technique in order to evaluate that integral. Ultimately, at the end of the day, this isn't terrible, right? Like if you can use the fundamental theorem of calculus and integration techniques to evaluate a finite integral, then all you have to do is take a limit to evaluate an infinite integral, right? Like it's not crazy. Okay. Any questions so far? Maybe let me get this proposition in case you wanted to give it a shot. Everyone's makes sense what we need to do here. Hopefully everyone's okay. Zoom in, enhance. How do I get the second line? So this one. Right. So I did the substitution, right? So I get here, maybe let me do that one a little bit slower. So I'm going to get the integral. So I don't have a t, right? I don't have a t dt. So that I get a half there for that reason. So I'm going to get 1/2 du. All right, that's the t dt all over u squared. And then I have to change the bounds, right? That's the important thing. So if I plug 0 into u, that's going to be 0 squared plus 1, which is 1. If I plug the upper bound of integration into this, that's b squared plus 1. That's how I got the bounds of integration. Right, and then I like pulled the half out, all that stuff. Does that make sense? Yeah. Yeah, and I know, right? We only did substitution on Tuesday, but like I'm already using it kind of full bore. And of course, if you didn't want to, right? Like if you didn't want to change the bounds of integration, you can, at this point, you can switch back to t and then use our original bounds. And that would totally be okay. You'd get the same answer. So if you don't want to change the bounds, you don't have to. That being said, if you don't want to change the bounds, make sure you just put a little placeholder there, right? Call them something different. Just don't use the same. Don't write 0 in B. But yeah, you can totally just change back if you don't want to change the bounds. And that's okay. Okie dokie. For the last line, should it be -1 or 1 right here? So, right, what I actually did, so again, I kind of cheated here. If I plug in, right, remember, you always got to plug in the top first. So that's -1 over b squared plus 1 minus -1 over 1. Right? So the kind of like dirty hack you can use here is if I take, once I've got that minus sign here, it says actually plug the bottom in first and then get rid of the minus sign, right? That's the same sort of thing that we used when we wrote down this thing, right? So yeah, so if you introduce the minus sign, you can switch the bounds around. So actually what you could have done instead is said this is the limit And, you know, I don't think this step is worth writing out, but it's something that you can use when you solve things yourself. So if I get rid of the minus sign, I can flip the bounds, right? And that's like that. So that's a nice little trick you can use, right? And again, I don't think it's necessarily worth writing out that step. Just be like, oh, there's a minus sign. I'm just going to flip the bounds and save yourself a little bit of time there. Okay, so that covers one side. Maybe I should have done a negative infinity, but it's the same thing, right? I think you know how to do it. Give it a shot if you want. It's not, you know, it's not scary. And these things show up all the time. They actually do show up in mathematics, and they show up a lot in physics, stuff like this. Even in my book, they talk about one of my favorite examples, which is when you're computing escape velocities. Like if you actually want to escape Earth's gravitational pull, in practice, right, the gravitational field extends to the edge of the universe, but, you know, obviously your calculations don't need to extend to the edge of the universe. So, but it's the sort of thing that because the gravitational field decreases proportional to your distance squared, that the numbers that you're integrating become so small so quickly, it doesn't really make a difference. So when you're computing escape velocities and escape energies from the, you know, from any gravitational well, you actually use an improper integral, right? So that's one of my like favorite examples, just because I'm a bit of an orbital mechanics nerd. But yeah, so they show up in real life. Real life being, you know, orbital mechanics. Now they show up in other places too. The Cashmere Effect. I feel like I feel like I've heard of it, but maybe describe it to me and I'll see if I can recall.
Right, it's like in space when there is a void between like two plates of steel, and like they stick together.
Okay. Yeah, I don't think I actually know about that off the top of my head.
But like what is interesting about that is that like there is a like inside of the Casimir like calculation for that, there was a sum of all the integer from 1 to infinity.
Okay.
And so in physics it's like when you have infinity it's bad. But then he found a way to transform this to -1/12.
Yeah, that
actually works.
That
Why?
BS. It's an analytic continuation argument, right? Like,
yeah, but what does it work in physics and not like in math?
Well, it does work in math, right? But this is another one of these examples of like the physicists doing things that they don't know they're allowed to do, and then it working out, right? Yeah, let me look into that calculation a bit. Now, I might be able to find a nicer justification for why this works, but it's the same sort of thing. Like as well, when you get into quantum field theory, like the whole issue with quantum field theory is there's infinities everywhere. And they do a whole bunch of like crazy nonsense to get the infinities to disappear. Just like the craziest nonsense, right? The quantum field theorists will be like, okay, there are a bunch of infinities here. Obviously, this is bad. So let's pretend this doesn't matter and do some computations. And then suddenly, and then experimentally, it all works out. And you're just like, no, why? Like you just made stuff up. You just arbitrarily assumed that you could ignore something and it happened to work out, but you have no idea why. Right? It's one of these issues. So maybe let me look into the calculation of the Cashmere Effect, because I don't, I don't know this calculation off the top of my head, so I don't have any insight about it. But maybe it comes out, because that sum of the positive integers thing, right, is an analytic continuation argument. And if you can make the argument that things are happening in the complex plane, you might be able to get away with it. But yeah, I don't know the mathematically rigorous argument for that. But that being said, there are lots of things that physicists do for which the mathematically rigorous argument is actually really, really hard, right? So we're not too worried about that. But yeah, okay, let me look at that. That's an interesting thing. Okay, so let me quickly do two-sided. I want to kind of get this one out of the way, and then we can focus next week on like just grinding out all the theorems that we need. So this time we're going to talk about the integral from negative infinity to infinity. And yeah, I mean, basically it's going to be, if you think about positive infinity as being one-sided limit, negative infinity being the other sided, then this is going to be a two-sided limit, right? So if f maps R to R, we'll say it's integrable if it's, again, integrable on any compact subset. We say it's integrable if f is integrable on AB for any A and B. Okay, it's improper integral. So we say that the integral from negative infinity to infinity of f converges if, and really it's like, it's a definition. So if you want, it's an if and only if there exists some point C in R such that the integral from negative infinity to C of f and the integral from C to infinity f exist, in which case this is their sum, right? As some sort of like additivity of domain thing. F plus the integral of C to infinity of f. And so their value is going to be their sum. Now, in practice, this says there exists such a C, right? And there's a couple of things that we would need to check here. And not everyone defines it this way. For example, I think Spivak just says, just takes C to be 0, right? And just says, hey, listen, see if the integral from 0 to infinity and from negative infinity to 0, if those both exist, you're done. But morally speaking, there's nothing special about the number 0 here. So I like this definition a little bit more because it's a little bit more flexible. But that being said, that comes with a cost, and namely that cost is 1, is that we need to check that the value of C does not matter. Right? In the sense that if it works for one C, it'll work for any other C. Okay? And 2, check that if it works for one C, it works for all C. I'm going to leave these proofs to you. They're very straightforward to do. Okay, it basically is really an additivity of domain argument, right? So if you know that it works for some C and you choose some other number, let's say D, the only thing that changes is that these two integrals, the integral from negative infinity to C and from C to infinity, just shift over a little bit, right? Like they pick up a constant. In one case, you add a constant. In the other case, you subtract a constant. And that constant is just the integral from C to D, right? So one of them gets that added to it. The other one gets that subtracted to it. And then when you add them together, you get the same number, right? As you did originally. So that proof is very easy. And that actually basically proves 1 and 2 simultaneously. So it ends up, yes. Yeah, exactly. Yeah, and you kind of caught that, is that they are basically the equivalent statement. So that proof does do them both, right? Because you're saying like, hey, listen, if the value of C doesn't matter, then I can use any value of C. And once I have a value of C that works, well, clearly all the other values have to work as well, in part because you're integrating on the entire real line, right? So if one number works, obviously any other number has to work as well. Proof's pretty easy. Like I said, I'm going to let you kind of work it out. Let me do a quick example of how we compute it. Obviously, it's not too much work. It's just like, well, I guess it's twice as much work as a one-sided one, right? So let's do something like the integral, let's say determine. So far, I've given you only examples of things that actually converge, but that's actually rare, right? If you just wrote down an arbitrary function, it actually wouldn't converge. Okay, so we can do something like e to the negative absolute value of t dt. And the absolute value there is to guarantee that we actually converge in both directions, right? Because if it's just e to the t or e to the negative t, great, we converge in one direction, but in the other direction, we our function explodes and gets arbitrarily big, and then we're in trouble. Okay, so solution, right? Let's use 0. So let's use c equals 0. So we're gonna, first thing, let's check this thing. So that's going to be the limit as b goes to infinity, 0 to b. Now, the benefit, of course, here of using 0 is that on the integral from 0 to b, we've always assumed that, we're positive, so I can just drop the absolute value. Oops, b goes to infinity. So that's negative e to the negative t. And of course, I'm going to do my trick again where I see that minus sign. So I'm just going to flip everything around. B goes to 0, 1 minus e to the negative b. And that is, of course, equal to 1. Now, in this case, I'm a little bit lazy. I'm going to say, yeah, this function is evidently even. And I realize now, actually, I don't think we actually proved that, but I'm going to leave it for you. And so this integral is equal to 2, right? Okay, and here I did use a fact, the following fact. So if f is even, then the integral from negative L to L of f is 2 times the integral from 0 to L of f. Or okay. And exactly. And if it's odd, the integral is 0. Okay. And you can all check these. This is just substitution. Okay. The proof is 100%. Just break your interval into negative L to 0, 0 to L, apply a substitution, and it works out, right? So use substitution and give those a shot. So I've given you a couple things now that you have to check. Okay, so there are a few things. What's in our to-do list here? Okay, so the first thing I think was this one. Try this as an exercise, because up until now, right, all we've done is what? I've defined some things and we did some computation. This is kind of like a first proof, and in some sense, this is one of the easiest proofs I could give you. There is one result that we're going to do, which is slightly easier, which is called the p-test, and the p-test is very easy, but it's not like for drugs or anything. So, do this one, try this one as an example, and then just here, double check that the value of c doesn't matter, right? And that if it works for one value of c, it works for all values of c. And then just quickly verify these facts, which actually are not related to improper integrals at all. This is just substitution. And actually, it's possible to prove this without substitution. It's possible to prove this just using the Darboux definition of the integral, but it's much easier with substitution. It becomes a very straightforward thing. So you can do it that way. The only thing, let me kind of finish off by saying the following. The benefit of not having to use c equals 0, so you can see here I did use it, but you can imagine if I had asked you to do something slightly different, like what if I'd said do the integral from negative infinity to infinity, e to the negative, t plus 7 dt, right? Like this obviously still exists and is the exact same answer, right? When you do this, you're also going to get a number 2, because this function is just the original function, but I slid it over to the left 7 places, right? So it should give me the exact same value. And if you want, do this computation and check. But when I do this, when I split this one up, I don't want to have to use 0, right? I would prefer to use probably -7 as the point at which I split into my two one-sided improper integrals, because that's where the absolute value is going to be easiest to drop, right? Rather than having to be like, oh, let's look at 0. Okay, if I'm less than 0, then I have to now break that into where I'm less than -7 and where I'm between -7 and 0. And that's a big pain in the butt. So the benefit of my definition over, say, Spivak's is that you can just use whatever point you want. But again, that comes with a price, and that price is the exercise at the top of the screen, right? But that exercise is very simple. Okay. So give those a shot. I've posted your next homework as well, but that homework is, I think all things considered, is probably on the easier side. That being said, like, don't, I say that, but there is a little bit of a trick to doing both of them. So you do have to think about them for a little bit. It's not just like, to close your eyes and compute. It's not quite that easy. But there is a little trick for both of them. It's not terribly hard. Give it a shot and see where you can come. Obviously focus on your current homework first, but that's, thinking for next week. And yeah, that's going to cover it for today. Let me think about this Cashmere effect and see if I can, make sense of it, because I feel like I've probably heard of it, but this sum of the positive integers being -1/12 is one of my most hated things in the world, because I know that it was big on YouTube for a while. And on the one sense, great, because it kind of got people into math. But on the other hand, I think it's actually done a lot of damage, that result, because anyone who thinks about that result, it's obvious that it's nonsense, right? Unless you know, for example, about like analytic continuation and stuff like this. And so in some sense, it's actually done damage to math. Anyway, whatever. That's just my personal opinion about that whole, trend of that having taken off. But whatever, it is what it is. Okay. Any other questions? Otherwise, I think we're done. We can call it. You guys can have that 3 minutes for free. Or alternatively, maybe I'm screwing you out of 3 minutes that you paid for, but who knows? Yeah. All right, everyone. Thanks so much. Like I said, have a good weekend. Yeah, you can ask the registrar. Go to the registrar, tell them that I finished class 2.5 minutes early and that you demand your money back. Please record it, because I want to see how that interaction goes. Yeah, otherwise, hopefully I will have it. Sure, yeah, I could talk about it, but I wouldn't get anything done. Yeah, go ask the registrar for that. Like I said, I really want to see how that interaction goes. What is a sequence? I mean, a sequence is just a map from N to Z. Literally, that's the definition of a sequence, right? A sequence is, or N to R. That's what a sequence is. There you go. There's your crash course into sequences. Yeah, it'd be good to go. Now tell me what a subsequence is, right? Crash course in differential form. I can't even crash course differential forms. It's too hard. It's too hard, right? It is a map from whatever space you're working in. Let's say we're doing it in one dimension. So we're doing it differential forms in R. So we get very lucky in R, because the top exterior algebra of R is just R itself, right? So nothing like weird happens there. We get very lucky that this is true, which tends to mask a lot of the stuff that happens. But then basically a differential form is a map. What do I want to call it? Let's call it like this. From R into a whole bunch of, well, actually, I guess even we can't even detect, it really should be this. Which we know is just isomorphic to. Right, one of these things. But then, like, that's not even that crazy. I guess I should really just even say like this is kind of boring because we don't actually learn anything from that. So really it's just a map, I guess, from R to R. Maybe differential forms in one dimension aren't too bad just because everything cancels out. But in multiple dimensions, we'd going to start to get interesting because we don't even have a wedge product here. So in one dimension, they're really, really boring. For Duram, so Duram though is like this, right? And is integration by parts related to differential forms? Not really. Duram's theorem is more complicated than that, right? Duram's theorem says that the singular cohomology and Duram cohomology are the same, right? That's Duram's theorem. And to understand that, you need to first of all know what Duram cohomology is. And yes, you're kind of on the right path. You need to know what a differential form is to even get the Duram cohomology. But then I'd also have to explain to you what singular cohomology is, and that's a whole different bucket of nonsense. Like of what cochains and co-boundaries are. Not even chains and boundaries, cochains and co-boundaries, right? Because differential forms form a cohomology, not a homology. So, right, that's something else that we have to worry about. Okay. Yeah, hey, look, we made it. Way to go. Yeah, there you go. Now nobody gets a refund. All right, everyone, have a good weekend. And yeah, I'll see you on Monday and or Tuesday. All right, bye, everyone.